They're afraid to go outside now.
I work down the street. That was over the weekend, the south end of the North England, where the doors are. We caught fire.
So did they find the cause of the fire?
No, not yet.
Oh.
Well, they, when they left, they kind of just left. They haven't done anything with it because they don't want to go in.
Right.
But it's still collapsing and burning, and because it's the west side of the hangar now. It's
right. Yeah.
Is it going to be a binder?
Were you here when we talked about the final project? So go watch that lecture. It's basically an extra problem for the final project. Yeah.
So it's the west side of the hangar now that's on fire.
Oh my goodness. Asbestos flying everywhere.
Well, you know what asbestos was designed for?
What?
An adiabatic material.
Oh, those have the best toxins, even though they're supposed to resist heat.
Well, it's doing what it was designed to do, retain the heat.
Oh, yeah, that's one way to look at it.
So it retained the heat when it caught on fire from last week.
And it's still burning this week.
Yes, it is. They're saying it's going to burn for a while.
Oh my goodness.
What they needed to do is, well, either way, it's a double-edged sword. Either you just knock it down and you let it burn, or you throw flares on it and make it burn faster. Either way, it's still not great because you're now burning all that asbestos still. But you could say,
it's a bad situation. My friend was saying that what they're telling everyone is that once it rains and stuff, all the asbestos is in the air that's going to soak into the soil. And so he's not going to eat fruit from his garden for probably the next 10 years.
Yeah. At least we still have the South anger. Hopefully we can keep that homeless happy. That was really great. I'm trying to think what you've done. This was from yesterday.
Wow. Black smoke is never a good thing.
No, that just shows because I'm on Tustin Ranch Road. And the hangar's all the way on the other side.
Oh wow.
That's how big they are.
That's crazy. Between that and the fire on the 10th freeway, it's crazy.
I took this last week on Thursday. This one. I was right by it, that one.
Dang.
Yeah, because the North Hanger is off of Armstrong, Valencia. I would Armstrong after work, in between work and school, last week on Thursday. I got a text at work today. Fire again? Yeah, we need that. Fired up.
Yes, that's correct. Yeah, so the midterm is going to be in our usual lecture room, CS 304, at the usual lecture time at 5:30. Yeah. Or you can make take home. No, I want to grade them over the break. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Hanging in there. A few more days until Thanksgiving. So we're almost well, it's not the finish line, but it's it may as well be. I need a break. Okay, so this week is shortened, of course. So we have our midterm exam on Thursday. So please be here for that. So the midterm exam is going to take place in our normal lecture room, CS 304, and take place at 5:30. So it's going to go just during our normal lecture time. Okay. Okay. And so for today, I always say that this is probably the most forgotten lecture that you can possibly have this entire semester, because it's the lecture before midterm, before a break. And so we're not going to be able to see this again until after the Thanksgiving. And so but I chose kind of a very special topic today, something that doesn't directly have to do with finite elements. And so we're all done with the direct stiffness stuff. And so now we're kind of cleaning up the semester and talking about more kind of practical things with FEA, maybe some more advanced features that you guys want to see. And I think more importantly, after the break, maybe for the last lecture or two, I'm going to give you guys time to work on your projects in the class. Okay. But today we're going to talk about a topic called verification and validation. Sometimes it's called V&V, which is going to be something that's going to be part of your final project as well. So this is something that's going to be really, really important. Okay. Okay, so I've had a few people kind of ask me, when are we going to talk about the final project? You guys have basically done it already, and so the final project is going to be very similar to the midterm project. There's going to be small differences in terms of you're going to have to incorporate some verification and validation, and you can choose your own geometry. But I'm going to hold off until after the Thanksgiving before talking about the final project, just to kind of give you guys the mental space to kind of prepare for the midterm, and then after Thanksgiving, that's kind of the final rush towards the end of the semester. So we'll talk about it then. But for the most part, it's very similar to the midterm project, and so it's nothing too revolutionary or anything too new. It's just kind of doing kind of the same things for the midterm project, but with a different geometry. Okay. Okay, all right, and so that's all my announcements. Oh, I posted the solutions to problem set 1. That should be on Canvas, and so if you look at the page for week 13, it should be kind of at the bottom of the page there. Okay, and so on that problem set that I gave you guys, I actually took off a problem, the longest problem on there, and so but that one is part of the solution. And so if you wanted to see kind of a more complicated problem in terms of what it looks like, in terms of all the work that's involved, you can kind of think of that as kind of an additional work example. So make sure you kind of check that out if you're looking at the midterm, or excuse me, the problem set solutions. All right, are there any questions I can answer before we get started for today? Okay. Oh, question. Yes.
I have like the extra problem, like more difficult than the exam?
It's,
Kind of the same?
I mean, yeah, that extra problem on the problem set is certainly much longer than what I'm expected to do on the exam. But you know, the thing is with direct stiffness, it's the same process over and over again. It's just a lot of writing that goes into it. So, yeah, so that problem is definitely going to be much more complex than what I'm going to ask you to do. So, yeah, for sure.
One of the problems that would be your closest forms that we should really listen to?
You could probably expect anywhere between 3 and 4 elements for a problem, and anywhere between 4 and 5 nodes per problem. And there's 2 problems on the exam. I used to do 3, but when I did 3 problems on the exam, it was impossible for people to finish. So I'm cutting it down to 2 this year.
Okay.
Yep.
That's nice of you.
All right. Any other questions? Yes.
During an homework, I stuff like we have different young modules or whatever it may be. I noted which means which like with the subscript.
Mhm.
For the midterm, do you want to look for simplify one? Like let's say we have these divide by to cancel it out. Do you want like a closer simplified direct matrix, or can I get away with just writing like which ones to simplify it?
You can write subscripts. So anything that you want to kind of simplify it, and usually as long as your writing is neat, usually I can follow your work pretty well. And so as long as you're kind of neat and organized, and you can use kind of different variables, because it's a lot of writing. And so anything that you can do to kind of substitute. So like say like you can define a new variable. This is equal to EI over LQ,
Yeah.
just to kind of save you from writing EI over LQ. That's fine. So I can usually follow that just fine. So okay, yeah. Yeah.
The conceptual question would be from node 9, 10, 11, really?
Yes. Yeah. Yeah. Only the direct stiffness stuff. So none of the answer stuff. Yeah.
So like, how are you, I guess, like quantifying the points, is it like a point for like everything on the matrix?
No. So I mean, that would be insane. So I mean, I'm going to look at your whole process, and so you'll see on the exam, but I'm going to break it up into parts. So I'm going to say like, you know, write out all the element stiffness matrices, and that'll be worth, you know, a percentage of the points of that problem. Then write out the global stiffness matrix, and then apply the boundary conditions. And so you can assume that each part is worth a third of the points. And so based on how you execute that process, I know there's going to be small mistakes here and there just because these are big matrices, and you know you're on an exam, and it's kind of a time constraint thing. So I'm not going to check every single entry in the matrix, but if I can see that you're applying the method well, and it's just kind of small mathematical errors, I tend not to take any points off of that. Yeah. All right, any other questions about the exam?
So the last step in the problem would be applying the boundary condition, right?
Yes. Yeah. So I'm not going to ask you to solve any of the systems, and so boundary conditions will be the last step. Yeah. Okay. All right. So let's go ahead and get started today. And so the topic for today is called verification and validation. Okay. So verification and validation, this is, I think, a very interesting topic, and I would say one that may or may not be covered in every single introductory FEA course, but I think it's important, and it's an important aspect to, even though, you know, if you're going to be using a commercial software like ANSYS, for the most part, you're not going to be doing any explicit verification of validation. You know, it's still kind of important to kind of know that this process exists and kind of what the purpose of it is. Okay. So let me start by saying this, right? So we've been using finite elements throughout this entire course, right? So whether it be, and we've done it at kind of very different levels. And so we've done ANSYS, on very simple cases, we've done ANSYS on more complicated cases, we've gone over direct stiffness method, right? All of this kind of belongs to that realm of finite element simulations, okay? And so hopefully, you believe this at this point, but finite element simulations are a very valuable tool for the engineer, mostly because it lets you predict, things like deformations and stresses without actually having to run a physical test, okay? I say structural behavior, but of course FEA can be applied to the heat thermal analysis and fluid analysis as well. But I want to be a little bit more specific than just predict the behavior, right? So any kind of engineering behavior you can predict. Okay. And so up to this point, we've kind of been taking we've kind of been taking the results of our finite element simulations as kind of true, right? And so basically whatever we obtained from the simulation in terms of deformation, in terms of stress, right? We've kind of implicitly have believed that to be exactly what's going to happen in reality. Okay. Okay. But I want to caution you about that, right? And so even though we're spending so much time in this class and learning how to use FEA, right? At the end of the day, finite elements is nothing more than just a tool for you to perform your engineering work. Okay. And so specifically, finite element simulations are only approximate predictions of what could happen in reality. That's a very important point to remember, because I think especially when you're first running finite element simulations, you run a simulation and you think, oh, this is the gospel of engineering, right? So this is exactly what's going to happen. But there's a lot of things that can go wrong within a finite element simulation, and kind of the upshot of that is that your finite element simulation could give you wrong answers. Now, of course, we don't want it to be wrong, and so the idea is that we're spending all this time learning about meshing, material properties, boundary conditions, how to apply these in an intelligent way to make sure that it's not wrong. But at the same time, it's still possible for your FEA to be wrong. Okay, and you need to kind of take this into account, when you're running your simulations, that your predictions could be wrong. Okay, so FEA as a whole kind of belongs to kind of a greater class of tools that we call models. Okay. Okay. And a model is nothing more than a calculation or a prediction for reality. Okay. And of course, with that statement, FEA is not the only model that's out there. So there are a lot of different models in not even in just engineering, just in general. Okay. So let me give you an example. Okay. Just to kind of give you a sense of the scope of kind of what's considered a model. Okay. Let's say that we have a fairly standard FEA problem. So let's say that we have a beam. You have a cantilever beam, and let's say that we're applying a force at the end of the beam. Okay. So this may be a part of your structure, it may be something that you're simulating, whatever. Okay. And so let's say from this situation, we want to be able to predict the maximum equivalent stress that's going to occur in this beam as a result of these conditions. Okay. Okay. And so if I were to give you this problem right now, right, and I said you can use any tool at your disposal, right? I think what probably most people in this class would do was that, you boot up ANSYS, you create a geometry of a beam, you'd ask me kind of what are the dimensions, what are the lengths, the cross-section areas, and so on. You'll ask me what the force is, and then you'll run a very nice kind of finite element simulation to answer this question. Okay, we can say model one. Okay, simulate this in ANSYS. A totally valid approach. This is not a trick question, so that you'd be able to get a good answer from that. Okay. Okay. And so that kind of begs the question of what are some other ways that we can find this out without actually having to physically construct the beam, right? And so let me give you an example that you may not have been thinking of. Okay. Let's ask our 8-year-old cousin what he thinks of the situation. Okay. I have to update this every year because when I wrote these lecture notes, it was 4, so now he's 8. Okay, and so let's say that it's Christmas, you're visiting your aunt's place, and you have this on a paper. And it's like, all right, Jordan, I have this cantilever beam, right? It has these dimensions. I'm applying a force. What is the maximum stress in this beam? And what he does, he looks at the paper and he tells you maximum stress is 5. Okay. So then you ask your cousin, it's like 5 what? What are the units of this 5? And he's like 5. And then he runs away from you, and then he throws a Pokemon card at you. And so that's the end of that conversation. Okay. Okay. Believe it or not, as ridiculous as this sounds, this also counts as a model, right? Because this satisfies all the criteria that we use for models, right? It's a prediction of reality without having to actually run a physical test. Okay. And so on the one hand, you have a method which requires 15, 16 years of schooling. You have to go to a school with an engineering program. You have to get this bonding engineering program, take the finite element course, and then that's how you do that, right? The other method is your qualification as an 8-year-old. Okay, so obviously, from this example here, even though both of these are technically models, one model is obviously much better than the other one, right? And so we can kind of sum that up and say some models are better at predicting reality than others. Okay. So how do we know? How do we know which models are better at predicting reality than others? In this case, it's obvious, right? In this case, it's obvious, my 8-year-old cousin is better than ANSYS, right? But in some cases, it's not so obvious, right? Even between different simulations, right? So maybe you're running a finite element simulation on a coarse mesh versus a finite element simulation on a fine mesh, right? Intuitively, what we think is that the fine mesh simulation is going to be more accurate. But are there ways for us to kind of systematically and kind of and even kind of numerically show that one model is better than the others? Right? And the way that we prove this is through verification and validation. Okay. Okay. So verification and validation, these are things that you can do to kind of show that your model is an effective one. Okay. All right. Any questions on this so far? Okay. All right. So let's get into some definitions, right? And so I've given you two words here, right? Verification and validation. They are different. They get confused for each other quite often, but there is kind of an important distinction between them. Okay. So let's go ahead and define these terms more carefully. So let's start with verification. Okay. And so with verification, what this is assessing the numerical accuracy of a simulation relative to the solution of the underlying equations. Because usually when you're talking about, at least when you're talking about engineering models, right, they involve the solution to, oftentimes differential equations, partial differential equations, okay? And so part of that process is that, because it is really difficult to solve a partial differential equation, you have to do some approximation, you have to do something like FEA and come up with an approximate solution to those equations, okay? And so in that process of going from governing equations to your finite element solution, you may not even solve the equations correctly. Okay. So the way that I remember verification is to kind of ask myself the question, are we solving the equations correctly? Okay. Okay. All right. So the other piece of the puzzle is validation. Okay. So validation assesses the accuracy of a simulation relative to the physical phenomenon it's meant to model. Because every simulation at the end of the day, we're not just solving a math problem, right? And so at the end of the day, we're solving a problem that's meant to represent something in reality. Okay. And so validation assesses, how closely are our predictions relative to reality. Okay. And so just like verification, the way I think of validation is I think of, I kind of sum it up in just kind of one question. Okay. And so the one question that I think about when I think of validation is, are we solving the right equations? Okay. Question mark. Okay. Another one I think that's more relevant is did we even set up the problem correctly? Right, so that's the difference between verification and validation. So very similar. At the end of the day, they're both, going to be assessing accuracy. It's just that what you're exactly kind of what you're assessing relative to is different between the two. Okay. Okay, so let me give you an example. I'll give you an example of both, just so that just to kind of give you a sense of kind of what these are aiming to do. Okay. Right. So one thing that we talked about in the past, and some of you have already incorporated into your midterm project and your activities, which is great, which is the idea of a mesh convergence test. Okay. And so the idea with the mesh convergence test is that you're testing your simulation result on different meshes, right? Usually going from a very coarse mesh to a very fine mesh. So let's think about kind of what we're testing on in a mesh convergence test, and let's categorize it as either verification or validation. Okay. And so with the mesh convergence test, ideally when you set it up, you're not changing the boundary conditions and you're not changing the underlying equations, right? So you're still using the same, system, either static, structural, explicit dynamics, whatever. So you're keeping that the same, and you're keeping all the boundary conditions the same. Okay. And so the equations that you're solving for and the setup of the problem is the exact same between all your different tests, right? The only difference is going to be the mesh test. Okay. And what a lot of you have seen is that as you change the mesh density, your results are going to change, right? And so the only thing that's changing in between successive mesh entries is that your solution to the equations is different. Okay. Okay. And so since the underlying equations are not changing, right, mesh convergence test is a form of verification. Because by doing the mesh convergence test, what you're asking yourself essentially is, what is the mesh density that we need to solve these equations as accurately as possible. Okay. And so kind of going back to the question of verification of, are we solving these equations correctly? Do we have the mesh density to solve these equations as accurately as we can? Okay. So mesh convergence test is a very common form of verification, and one that I'm going to expect you to do on your final project. Okay. Okay. Any questions on this? Okay. Let's do an example of validation. Okay. So we haven't done any validation in the class yet. But because normally validation requires some kind of experimental measurements or some kind of observations in nature, right? Because if you go back to the definition of validation, right, we're assessing the accuracy of the simulation relative to the physical phenomenon. Okay. Okay. And so the most common form of validation that that's used is an actual what's called a validation experiment. Okay. Okay. So the idea with the validation experiment, and these are not often performed, and so I would say that these are actually quite rare. But usually these are performed when you're applying FEA to a very kind of niche, a very kind of a unique situation. Okay. For the most part, I think, well, some of you, I haven't looked at all your final projects yet or what you're planning to do. But for the most part in this class, you're not going to be in that realm of doing something really weird and unique with FEA. Okay. But when you are doing something and you're applying FEA to something that's kind of unique, you want to make sure that FEA is still able to model that correctly. Okay. So I'll give you an example of one thing that I actually worked on when I was in grad school. Okay. So when I was in grad school, I ran finite element simulations of the cardiovascular system. Right? And so I was running simulations of blood flow through blood vessels and hearts, basically. Okay. And so one of my projects, one of the projects that I worked on was a validation experiment on how accurately can we use finite elements to predict flow of blood inside the heart. Okay. The heart is kind of this I don't want to say $1 million problem, but it's definitely a difficult problem because, for the most part, we've kind of figured out flow in the greater vessels, because a blood vessel is basically just like a pipe. And so it's basically like plumbing. But for a heart, the heart is a very kind of complex geometry with a lot of kind of complex kind of inner workings. And so, for a long time, it's been really difficult to run a simulation that can really predict flow inside the heart really well. Okay. And so what we did was, we set it up in FEA, and we ran the simulation. And then at the same time, we collected measurements from kind of real people using MRIs. And what we did is we compared, the measurements of kind of the velocity and the flow rate and the pressures that we got from the person versus what we got in the simulation. Okay. And so what we did is we compared. And so that's the essence of a validation experiment. And so, you're going to take measurements, you're going to take data from reality. And so usually that comes in the form of an experiment. Sometimes it doesn't though. Sometimes you can just observe things and get data. And then you're going to see if you can reproduce that in simulations. Okay. So that's kind of the terminology that we use. Okay. And so if you can show that, if you can kind of prove that through a validation experiment, then that kind of gives you more confidence that if you were to apply finite element simulation, maybe on a different person's heart, you have a lot more confidence that what you're getting is actually close to reality. Okay. All right. And so that's kind of the idea with validation is that, we want to make sure that what we're predicting actually is physically consistent. Okay. All right. Any questions on this? Yeah. Let's talk offline about that. That's that's more kind of specific to the research. So yeah, I'm very happy to talk about it. I could talk hours about it. But if I talk hours about it now, then we're gonna run out of time. So
No problem.
that's fine.
That's fine.
Oh, I mean, then you guys are gonna be here until 9 o'clock. Right?
Oh, no, we'll just leave.
If you leave, I'm not gonna talk anymore. You guys are gonna leave. Okay. So these two examples here are kind of giving the idea of what verification and validation is. Okay. The good news for you guys is that, because you're using a commercial software, the vast majority of this work has been done for you. Okay. Okay. So that's why, I've kind of waited until now to bring this up, right? Because that's kind of not a very, it doesn't really inspire a lot of confidence. So, we're doing this end activity. By the way, it's probably wrong. So what you're doing, right? But when you're using a commercial software and if there's a team of engineers kind of behind it, kind of a big company behind it, they do a lot of these kind of experiments. They do a lot of these tests for you. Okay. And that's part of what you pay for. And so, ANSYS, I know no one in this class has paid for ANSYS, or at least I hope not. Part of what we pay for is we pay for that reliability. We pay for that kind of confidence that what we're getting is actually reliable. Okay. And so for the most part, there's not much that you have to do unless you're applying FDA to something kind of unique. Okay. And so, but the reason I'm kind of bringing this up is that, it's even though you're using a very reliable and very kind of trustworthy software, it's still possible for you to get FEA results that are incorrect. Okay. Okay. And so those cases have not really much to do with the software, but more just how you're using the software. Okay. And so this kind of boils down to kind of a lot of things that we've talked about in the class. And so things like mesh quality. Okay. Mesh quality. Okay. Maybe incorrect boundary conditions. Maybe wrong material properties. Okay. The list goes on, right? So there's still a lot of room for error, even though you're using the software that that maybe you didn't, but someone else paid a lot of money. Okay. And so kind of the idea, and so kind of the reason we're kind of talking about verification and validation is that, I want you guys to kind of learn about different ways that you can increase the confidence of your simulation. Okay. Because I will tell you that as someone that's used FEA, for a long time now, 10 years now, the number one challenge that you're going to face when you're kind of out there in the real world using FEA is not actually performing the FEA yourself. So performing the FEA yourself is fun. That's the fun part. That's the easy part. The difficult part is convincing other people that what you're getting in FEA is actually legit, actually believable. Okay. Okay. There's a saying that I like to talk about is that, usually if you're going to be doing engineering in any kind of research capacity, a lot, and so one path that you kind of go down, so you're either going to be a computations guy, you're going to be simulations, or you're going to do experiments. Okay. And so that's kind of the path. And some people do a little bit of both, but generally most people do mostly computations or mostly experiments. Okay. And so the saying goes that if you do simulations, if you do computations, then the saying is that nobody will believe your results except for you. Okay. If you do experiments, everyone will believe your results except for you, right? And so when you're doing computations, you have that's kind of your challenge is to kind of convince other people that you are actually correct. Okay. And if you do any kind of a oral presentation on finite element results to any professional, you will very quickly learn that is the case because they will find many ways to kind of question you. But that's part of the that's part of the experience. That's the and they have a right to kind of be skeptical. Okay. Okay. So what I want to talk about from here is what are some ways or what are some additional tests that you can perform on your finite element simulations to kind of increase the confidence or to show people that what you're getting is actually reliable. Yeah. Question.
Would showing these elements fall in verification or not?
It's part of it. And so if you do use shell and beam elements and you can show through a mesh convergence test that you're getting converged solutions, that's a way that you can verify your results. Yeah. Yeah, so verification validation is it's not anything new. You know, I'm kind of presenting it as kind of a new thing, but a lot of verification and validation is kind of taking everything else we've learned in the class and kind of presenting it as a way to kind of show that you are, you know, you actually kind of know what you're talking about. Okay. Okay. So let's talk a little bit more about mesh convergence tests. All right, so we've talked about mesh convergence tests, I think a couple times already. So I think some of you already know, but this is kind of the most common way that you can verify your results. Okay. Okay, because through a mesh convergence test, what you're aiming to show is that your results are mesh independent. Okay. And what mesh independence basically means is that it doesn't matter once you kind of reach a certain point, right? Once you kind of reach a certain kind of threshold on your mesh size, it doesn't matter if you kind of refine your mesh even more, because your result is going to be independent of that. Okay. All right. Because any errors that you have that are a result from a coarse mesh, we call these numerical errors, right? And so they aren't errors, physically, right? So a numerical error is not something that can occur in reality. It's just kind of an artifact of running a numerical simulation. Okay. And so another way that you can kind of say this is that by running a mesh convergence test, you want to show that you've minimized the amount of numerical errors in your solution. Okay. And so to run a mesh convergence test, basically you're gonna run your simulation at different mesh densities. Okay. So typically you start from the left-hand side. So you start from a coarse mesh, and so a mesh with a very large mesh size and a very small number of elements. And then what you're going to do is you're going to run the simulation again and again, gradually decreasing the element size, which will gradually increase the number of elements. Okay. And then once you do that, for each simulation, you're going to plot the evolution of some quantity of interest in your simulation. Okay. Okay, so typically your mesh convergence plot looks something like this. Okay. And so on the horizontal axis here, what I usually like to do is I like to do the number of elements. Okay. Okay. I've seen some cases where they do on the x-axis, they do like the inverse of the mesh size. Okay. So that'll work as well. You want to have some so the horizontal axis should be some indicator of, you know, the quality or the refinement of your mesh. Okay. And the vertical axis is going to be some quantity of interest. And so this is usually going to be some kind of stress usually, or maybe some kind of deformation. Okay. Okay. And so each dot on this plot here is going to represent the value of that quantity of interest from your simulation at different mesh densities. Okay. And so, you know, maybe you have something like this, right? And so typically what you're going to see is that for the lower, you know, for the lower number of elements for your coarse meshes, as you refine the mesh, your quantity of interest is going to change, right? It may increase, it may decrease, and so you know, it can do lots of different things. It may zigzag, okay? But eventually you're going to reach a point where this plot is going to kind of level out, okay? And so what the leveling out basically means that if you refine the mesh anymore in that region, you know, you're not going to see any, you know, any change in the result, okay? And so what you want is you want to choose a mesh, right? I think last time we talked about this, I said that, you know, you have to choose, you know, the mesh right when it starts leveling out. But technically speaking, you can choose any of these meshes here, right? So all of these will work. Okay. It's just that the leftmost point is going to be the cheapest one. And so that's generally kind of a good thing. Okay. Okay. And so for these 4 points here, we can kind of definitively say that we reached mesh independence. Okay. And so at that point, you know, we've you know, maybe not completely eliminated, but we've minimized as much as we can the numerical errors in your simulation. Okay. Because what the left side of the graph shows, this area here, okay. The reason your quantity of interest is changing with the mesh density is because the numerical errors here are high, right? And as we increase the mesh density, those errors are going down. Okay. So that's ideally what you should see in your mesh convergence test. Okay. Some of you have tried doing this on your ANSYS activities, and you may not observe this kind of nice behavior like this. Okay. So if you've tried to do a mesh convergence test before, you know, let's say that you have a situation that's kind of like this. Okay. Right. And so you're increasing the mesh density, you're increasing it, but your quantity of interest is also increasing, or maybe it's decreasing, right? But you don't reach any kind of convergence point. Okay. Okay. And so what do you do in the situation when your solution is not converging? Okay. All right. So this can happen for several different reasons. Okay. One reason could be that, you know, maybe the convergence point is somewhere further from this, right? And so maybe if you were to continue this graph and to run, you know, simulations on meshes that are even smaller or have even more elements, you know, maybe eventually you'll reach convergence. Okay. So this is particularly relevant for our class because, you know, there's a limitation to how many elements you can have in your mesh in the academic version of ANSYS. Okay. And so it could be that your simulation is kind of complex, where, you can't reach convergence within the limitations of the software, okay? Okay. And so I think, at least historically for your final projects, your final projects might be in this category because the geometries that you guys use for the final projects tend to be more complex than the midterm projects. Okay. And so you may have a situation where you're just not able to reach convergence just because it's a little bit too complicated. Okay. That's okay. And so, for your final project, I'm not looking for you to reach convergence, right? Especially if you have a complicated case. But I at least want you to show these results. Okay. Because one thing that you can report is that, you can, in your report, you can display a graph like this, and you can say that you push the result, or you push the mesh as far as it could, but the convergence point is probably somewhere to the right. Okay. And that's an important thing to admit in your report. Okay. And believe it or not, a lot of practical problems are kind of in this regime as well. Okay. There's a never-ending quest for more computational power. And so, there are some problems that, are actually really, really difficult to solve, if not outright impossible to solve, just because we don't have the computational power, we don't have the mesh density to do it. Okay. One example that I was thinking about recently was turbulence. And so, in the world of computational fluid dynamics, turbulence is notoriously very, 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 very difficult to simulate. And so if you actually want to do turbulence really well, you need a very refined mesh. And I'm literally talking billions of elements if you want to do it well. And so in that case, there's not enough computers in the world to simulate turbulence. So it's possible. And so there's definitely lots of problems like that out there in the world. Okay. So that's definitely one possibility, is that, if you're not reaching convergence, maybe it's just, you just need more elements that you just can't support in the current software. Okay. Another reason this may be occurring, and this is kind of more specific to the structural FEA, is that you may have stress concentration at a sharp corner in your geometry. Okay. So we're kind of getting off topic a little bit. So this doesn't strictly have to do with verification and validation. It just comes up quite often in this class. So I wanted to mention. Okay. Okay. And so what this basically means is that if you have a geometry that has a sharp corner like this, okay, basically like a 90-degree angle. Okay. What can happen at the corner here is that no matter how much you refine your mesh, your stress there is going to magnify. Okay. And so if you have a geometry like this and you're trying to run a mesh convergence test, it may give the impression that your stress is just kind of increasing without any balance. Okay. And so I want you guys to be on the lookout for this. And so, this is something that you actually can fix. Because what you need to do is that, you generally want to avoid sharp corners in your geometry because of this mesh concentration factor. Okay. And so to fix this, you would have to modify the geometry so that instead of a sharp corner, you kind of add like a nice kind of round to it, a nice fillet. Okay. Okay. And that can kind of help with that magnification. Okay. And so if you have a geometry with sharp corners and you're not getting convergence on the stress, you may have to modify your geometry. So if you add a fillet like this, even something that's artificial. So, maybe in the real geometry, you don't have that, you actually have a sharp corner there, for whatever reason, okay? You may have to artificially add a fillet here just to make sure that your stress can converge, okay? So I mentioned this one in particular because this kind of happens every year to a handful of the projects, and so I want to make sure I talk about it today. Okay. Any questions on this? Yeah.
So if you do a mesh convergence test and you find a convergence point, and then you do something like change the material, do you have to redo it, or is it still like valid?
So technically speaking, any change that you make to the materials or boundary conditions, you should rerun your mesh convergence test. But for our cases, because we're working with mostly linear materials with linear equations, we can expect it generally to converge in the same place, unless it's a big change. And so unless you're going from steel to like I don't know, rubber or something like that, then if you're going from steel to aluminum, I would still expect it to converge in the same place. But a big change in material, I would rerun the convergence test. Yeah. Yeah, good question. Okay. All right, so that's verification. So that's something that's going to be a part of the final project. So definitely look forward to that. Okay. The other forms of verification that you normally don't have to do kind of mostly come during development of software. So for the most part, actually, verification is more for people that are developing their own code, or for basically the people that work in ANSYS. Okay. So in this class, we're not developing our own code. We're not programming anything in ANSYS, and so we don't have to worry about this. But I did want to mention that where if you do kind of move on from here and you end up working at ANSYS, work on developing finite element code, this is something that you have to do. And the main point of this is to kind of root out any kind of syntax errors that you may make in the code. Okay. And when you're writing a code as complex as an FEA code, those syntax errors happen a lot. Right. You'd be surprised. I found bugs in codes that were supposed to be all settled by the 70s. And so I've used a code that was developed in the 70s, and I found a bug in it that was causing not a big issue, but kind of a somewhat minor issue. And so when you have kind of these massive codes, then then bugs are just bound to happen. And so having thorough verification tests, having thorough kind of code testing is something that's really important. Okay, so let's talk about validation, okay, for the last 15 minutes of class today. All right. So if you want to do proper validation, you have to do a validation experiment, kind of like what we talked about at the beginning of class, okay? The reality is that, for the most part, most people are not going to have the time and resources to run a validation experiment, okay? And so, ANSYS does some of this for you as well, okay? And so commercial softwares, as part of their development process, is that they're running some validation experiments on some common cases, so situations that happen fairly commonly in engineering. Okay. And so you almost never have to worry about that. You almost never have to say, I'm going to run a validation experiment to increase the confidence in my results. Okay. It would certainly help. And so it definitely would help to do that, but it's definitely not a requirement, because the expectation is that the company is going to do a lot of that for you. Okay. But it still pays to have some kind of validation in your in your results. Just to remember, the whole point is kind of increase confidence in your simulations. Okay. So then the question becomes, how do we do any kind of validation without real life measurements? Because that kind of seems like a paradox. Okay. So technically, the answer to this question is no. And so if you don't have real life measurements, you technically can't call it validation, right? Because the whole point of validation is to see if your simulation is consistent with reality. And so if you don't have any measurements from reality, you technically can't call it validation. Okay. But with that said, there are still things that you can do to increase the confidence in your simulation. Okay. So I don't call it strictly validation. I call it sanity check instead. Okay. Okay. So sanity checking is a good practice to get into kind of no matter what field of engineering that you're in, right? Because you want to make sure that, when you're doing a certain method, you're doing a certain technique, you're not just relying solely on that technique, right? You kind of check against a different technique or a different kind of a thing to make sure that what you're getting is consistent. Okay. Okay. So for a sanity check, the way that we're going to do this, and the way that we're going to do this for the final project is that we're going to compare your simulation results to a different model or a different equation. Okay. Okay. And so what I usually like to call this is I like to call this the simplified model comparison. So I call it the simplified model because more than likely, kind of what you're going to do or what you're going to do for the final project is finite elements is probably going to be the most complex model that you're going to use. Okay. And so for the simplified model, I want you to kind of, do a computation that, ideally should be on the same geometry, on the same situation, and then compare what you've got on the simplified model versus the FEA simulation. Okay. So that's a very kind of vague description because, every simplified model is going to be a little bit different. Okay. But I think the easiest way to kind of illustrate this is with an example. Okay. So let's consider our cantilever beam from before. We have a beam that's fixed to a wall on one side. We're going to apply a force on the other side. Okay. And we can get a result. And so if we run a simulation on this, we'd be able to obtain the deformation and stress within the beam. So that would be one model that you can use to answer this question, right? So model one would be FEA. Okay. Okay. What if we did the same calculation with a different model? Okay, and I mean an actual model, so not asking your 8-year-old cousin. That was a joke. So don't. I don't want anyone's report to say, oh, I asked my 8-year-old cousin what this was, and he gave me this, and I'm validated. No, do an actual calculation for this. Okay. And so maybe another model that you can use for this is you can solve the beam equations. And so maybe you solve these beam equations by hand, and then that gives you a sense of kind of what the deformation and stress is going to be. Okay. And so for the beam equations, we have EA, E squared U, dx squared, okay, B of x equal to 0. Okay. So maybe you solve that by hand, and then you obtain a result for the deformation, and you can compare that to your FEA simulation. Okay. Another example, we'll call this model 3. Okay. Okay. Maybe you use the direct stiffness method. Okay. And so through the direct stiffness method, you'll be able to obtain kind of answers for the deformation and the stress within the beam as well. Okay. All right, so there's lots you can do in this kind of simplified case. Okay. And so the idea is that, to perform the sanity check, you're going to compare what you got for the deformation in your FEA simulation model 1 to what you obtained in model 2 or model 3. Okay. Ideally, if your sanity check is going to pass, all 3 of these models should give you the same or similar results. Okay. Okay. And so if that's the case, then you can say that your model is validated. Okay. Or not validated. It passed the sanity check. Okay. Because if you get the same answer using 2 different techniques, then it makes it all the more likely that that answer is correct. Okay, that's the idea. It's possible that both your methods are wrong. That is possible, but it's a lot less likely for 2 independent things to be wrong than it is for 1 independent thing to be wrong. Okay. Okay, so this right here is going to be an aspect of your final project as well. And so I want you guys to perform a sanity check calculation. What that sanity check is going to be, it's going to depend on your model. Okay. It's going to depend on your geometry. And I will say that, for most of your final projects, it's probably the geometry and boundary conditions are probably too complicated to run something very simple like this. Okay. Feel free to do a sanity check on just one aspect of your geometry. So maybe just a subsystem, maybe a subsystem that looks like a beam or looks like a truss, right? And that would be perfectly fine. Okay. Or if you actually do have some measurements, because I know some of you have already kind of started conducting work on your senior design projects. If you do actually have measurements under certain conditions, definitely feel free to use that as well for the final project. Okay. The point of this is that I want you guys to not just run the FEA simulation. I want you guys to check your results against something to make sure that it's reliable. Okay. We're going to talk about this a lot more after the Thanksgiving, but I at least wanted to give you guys a preview today. Okay. All right. Any other questions on this? Okay. All right. So let's wrap it up a little bit early, just because we have the midterm on Thursday. So remember, midterm is going to be here in class on Thursday. So please come in person. The exam will not be offered over Zoom or virtually in any capacity. So you need to be here. Remember, you can bring a writing utensil. You can bring your calculator. Definitely bring your calculator. The calculator is going to help a lot. And you can bring 1 cheat sheet. And so your cheat sheet is 1 8.5 by 11 sheet of notes. You can use both sides. You can write it. You can type it. You can put whatever you want on it. You can put example problems, summaries of the notes, whatever. Right. And so that's up to you. All right. So thank you guys for coming today. And I will see you guys all on Thursday.
We had this one, but also Saturday.
Oh, wait, how big is it?
Two-17.
Oh, wow.
You left the library?
Wait, you were flying it?
No, they flew over my house.
Oh, okay. Yeah, that's why it's orange.
Yeah.
You know, yes,
Oh, so
yeah.
there won't be like a quadratic versus.
No.
Or shall it be? or anything?
No, it's all from directed. So starting
So
from
it's just the
spring,
homework.
yeah, just the homework, basically.
Okay, very cool.
Yeah.
Why do you get?
Take mine.
Let me ask you about that. Okay, so, you go.
Sure.
Yeah.
Let me pull it up here. I have Dropbox here.
You go to the last row.
Okay. Mhm. Yep.
So for we do the integration, why is this from 0 to 9, not from 9 to 18?
Yeah, no, it's a good question. So this function right here, specifically this u of y function here.
Mhm.
You know, this function is defined with the assumption that you start from x is equal to 0.
Okay,
Because the way that it's formed, I don't know if I have the full form of it. I guess I have it right here, right? So this form of the equation right here is 2 over L cubed u1 minus u2.
Mhm.
That implicitly assumes that the starting x is 0.
okay,
And so even though this starts over here, you're still going to start the integration from 0
got it.
and integrate it to the total length of the
Okay.
of the b.
Got it.
We did that.
Yeah, I did it from 9 to 18.
Oh, yeah.
I was like,
Yeah.
take 2 pages.
Yeah, that's and doing it from 0 also saves you a little bit of work. When
It
you
does,
plug in
it does,
0,
yeah.
it cancels out a lot of stuff.
And then for even for we did the boundary conditions for these.
Mhm.
So typically, since this is fixed, right?
Yep.
So this line turn goes to 0.
Yep. Mhm.
This one goes to 0.
Yep.
And this one goes to 0.
No, just the first two, because for the beam, remember, we only have 2 degrees of freedom per node, and so we
Oh,
only
okay.
have the transverse displacement and the rotation.
Okay.
Yeah.
And then I have one other question. Oh, here's the one you had is 3, right? Because
Yep.
so this one's fixed too.
Yes. Yeah.
Okay, that's
Mhm.
what that's good.
Oh yeah. So this one, the first 3 lines are 0. Yeah.
Sure.
Mhm.
And then when you're doing plug-in boundary conditions, the force, you only apply the force at the node where everything else is 0.
Exactly. Yeah. Yeah. Mhm. What's up? Yeah, that's gonna be challenging. So there, I see a lot of small details on this. So you're probably gonna have to simplify it. I think the first thing you can do to simplify is probably suppress a lot of the empty parts. So the question I would ask them is, which aspect of this geometry you're going to be doing most of the flow in? Gotcha. So let's suppress everything else except for that, because even that by itself is probably gonna be another challenge. Well, you can do it manually, so go to the geometry. Click the process. So you have all these different parts here. So you're gonna right click, so once you press, right click
Yeah, and then,
Normally, when you right click on it brings up a menu where you can actually suppress the part. And there's a shortcut where if you want to suppress everything except the one part, you can go to that button and there's a button here to suppress everything else. I'm not sure why it's not showing up. Actually, right click in general. Right click in general. Usually when you write this stuff, you do more. But that's generally how you would do it. It's basically the same as that. Where you would, basically go to the and write it, and then you know, I trust everything except for the yeah, so the reason for that is because if you think of a small element size, because it's a small element, and then it's gonna be. So this, even just this arm beyond a color here is gonna be difficult to mesh, because there's kind of a lot of I think you should be able to do it, it's just gonna be a little bit, like a challenge. So if you want, what you can do is, try to reduce the size. This one is present, so there's that equity. Okay. Not sure how to do this. Because right now, because usually when you write. Yeah, good idea. Okay, yeah, why don't you try that, and then, yeah, try to restart, if you restart, if you want, try all the other features. I would start with that, and then try to get a simulation going with that, and try to add the other parts of the after. That makes sense. Want to kind of add
Alright, I'm switching, so this is for buying again.
Okay.
What is for doing? Okay. Yeah. And it's all the way around. Would we need this angle in between here, so 360 minus the or can we just create a view as the angle?
Usually I just use these.
Okay.
Because that angle is defined relative to the horizontal.
Right.
And so that angle, because we're not using that angle by itself, we're always taking the sine and cosine.
Right.
And so the sine and cosine should take care of any kind of sine.
Okay, yeah, I wasn't sure if there were any kinematics one had like a linkage like that.
Yeah.
So, okay, thanks.
Yep.
You want the last? Yeah. So how long did it take you the recommendation for the running the company?
Oh, how long? Oh, it depends. Sometimes it could be a couple of days. Obviously, sometimes it could be a couple of it depends a lot on the measure.
How do you have them access?
Yeah, there's ways to do that. If you are doing research under like a national grid, then they give you basically a way to log in. Yep. Okay. Okay, so let's try to manage overall life. So let's reduce this mesh size. Let's try. So the thing with the mesh is that you can mesh it to be as small as you want. Granted, that doesn't work. The thing is, like, if you have the mesh elements that are greater than the you could actually reduce 0.2. Let me do. When I see things like this, basically that it's this tells me that the element size might be a little too big. So we have really big elements here and really small things.
Yeah.
So we may have to reduce the mesh size. But yeah, the challenge that you have is that there's so many parts. We can see that it's kind of counting all the different surfaces. So kind of highlighting that individually and trying to find a mesh that's kind of consistent with all these things. Yeah. It's gonna be challenging. This is kind of a challenging challenge. So I think we should be able to do it. Just kind of talk about competition. You guys have questions in the meantime?
Yeah, quick question. Oh, you wanna go first? That's a quick question about the midterm.
Yeah.
Or as the conceptual go, is it gonna be based on kind of like how we did it like on the problem set or more so like the entire semester?
It's just on the problem, set, so it's gonna be just on the direct state.
Oh, okay.
Yeah.
Alright, cool.
Yep.
Pretty-
Okay. Haven't froze yet. Like, how much more you guys can do? This one isn't super active here, just because, this step kind of takes a long time. Besides that, as long as it's still kind of highlighting circles, it's trying to do something. And so it's, you just kind of have to just kind of write it. And so usually if I don't see things highlighted, if I try to match something like more than like 20 minutes, then I'm usually kill it. But it looks like it's an easy five. So let me, but it's five for witness.